so this time we're going to try to work with explicit functions instead of recursive functions. We've got two examples here. These are both arithmetic sequences that we're going to work on for now. I'll do another video with geometric sequences here in a few minutes. Now, when you write an explicit function, just like when you write a recursive function, you have to know what the pattern is doing. So we're going to start with that. Since I've already given us the hint on this one that it was arithmetic, then I know that these are adding the same amount every step. So I'm going to use that next minus previous. 19.9 minus 16.5 is a 3.4 rate of change or common difference, whichever word you prefer. So as I look at this, it's going to keep going down by 3, or up by 3.4, I guess it is. These are positive change. Up by 3.4 every step. Now, when I go to write an explicit function, this is different from the recursive function. Remember, the recursive function took 2 lines, one to tell you where to start, and a second line to tell you what to do next. Explicit functions take all that information and smush it together in just one equation. So I'm going to be able to find the next term, f of n, using just this one line of information. Now in this pattern, it started from the number 16.5. So rather than saying f of 1 equals 16.5, I'm going to say f of n equals 16.5. And then I'm going to tell it to do stuff to that 16.5 right in this same line. So since I know that this pattern is going up by 3.4, I'm going to add 3.4 onto it. But I don't want to just add that 3.4 on once, because it adds it on once to get to there, a second time, a third time. So notice the number of times I add that 3.4 on matches with the term number. Term number 1 I get when I add 3.4 on once. Term number 2 I get when I add 3.4 on twice. Starting from the 16.5, I had to add it on twice to get to there. Or the third term would add 3.4 on 3 times by the time I get to that point. So to show that I'm going to add 3.4 on over and over again, n number of times, I'm going to put times n here behind this. And then I need my domain behind that. This tells me start at 16.5, add 3.4 on every single step I take. Now, with this problem, we start up here with term 0. And if I were to put 0 in here for n, it would be 16.5 plus 3 times 0. So I can use this to get the 0 term. So unlike with the previous type, the recursively defined functions, when I write the domain for this explicitly defined function, I say n is greater than or equal to 0, because I can have term 0 put in there, and it does give me the value. With the arithmetic, recursive ones, you had a separate line that told you that starting term, so you only use the bottom line for terms after that. With this one, we're using this line for every single term that there is. So n is greater than or equal to 0 because we started on term 0. It also asked us to use that to find term number 5. Well, remember, n here is my term number. So if I want to find term number 5, that just means I take this equation and put in 5 as the n. So I've got f of 5 equals 16.5 plus 3.4, and then my times n becomes times 5. Order of operations tells me to multiply these first. 3.4 times 5, that's 17. Add that with the 16.5, and you would get 33.5 for f of 5. So in other words, that's telling us the value for term 5 is 33.5. And if I kept going here and adding 3.4 on 2 more steps, just estimating, yeah, that would be pretty close to the right answer. That's a reasonable result. So that's the first example. The second example is just a little bit different because we have, starting from term number 1 is 70, term 2 is 66, term 3 is 62, and term 4 is 58. It is still an arithmetic sequence. In fact, this one's a pretty easy one to figure out. It's subtracting 4 over and over again. Remember, next minus previous could have told you that if you got stuck. Let's try to write the explicit function for this one. It's going to start with f of n again, or I guess maybe on this one, since they were calling this function g, I'll change that to g of n. Now, since I want to put the entire thing in one big problem here, I'm going to use g of n equals 70. That's where we started. And then this one was going down by 4. Now, behind this, we would normally put times n because we want to see how many times we subtracted that 4. But this one's a little trickier. And the reason it's trickier is because of this right here. We started counting with term 1. So if I put 1 here, that would tell me that term 1 was 70 minus 4 once. But I don't need to subtract 4 from 70 to get 70. In fact, I don't want to subtract any 4s yet. So what I'm going to multiply that 4 by this time is n minus 1. So that way, if I put in term number 1, this would say subtract 4 0 times. If I put in term 2, then this would be 2 minus 1 or 1, so we'd subtract 4 only once. Term 3, notice I subtracted 2 4s to get there. This would be 3 minus 1 or 2, so we'd say 70 minus 4 twice. And then my domain, n is greater than or equal to 1, because the sequence started from 1 this time. So that right there is the explicit formula. And then this one also asked me to use the explicit formula to find term number 12. So that would be g of 12 equals 70 minus 4. And then I put in 12 for n, so 12 minus 1 becomes 11. 70 minus 4 times 11. Because to get to term number 12, we would have only subtracted 4 11 times. That would become 70 minus 44. Let's see. 70 minus 40 is 30, so this would be 26. G of 12 equals 26. Means if I were to continue this sequence out to term number 12, it would be the number 26. And you could keep that going as far as you wanted in the future by just choosing a different number for your term number and just plug it into that function and you can get the output for that term number. These are much easier to work with than the recursive functions because these don't require you to repeat that step over and over again. You can just put in a number as the input and it will tell you the value of that term.